I found out like yesterday afternoon that I had to do this talk, so I was preparing. So I didn't get a chance to see the keynote. I look forward to watching the video of it. Hi, my name's Richard Campbell. I am an old geek. I've been doing this stuff for a long time. I'm from British Columbia. This is a picture of my house on the left and my neighbor's house on the right. We call this the Animal Highway. I didn't realize until I put this camera in that we get bears every week. This is about 6 in the morning in the summertime on a Wednesday, because Wednesday in my neighborhood is garbage day. So he's just coming to see if I put out my garbage early or not. And there are consequences if I do. So, and actually we get fined if we put out the garbage early. It's quite against the rules, but that's what it's like to live in British Columbia. It's just forest behind me. It's like a big old buffet for bears. And they come through and check on us. You see he's actually at the top of the driveway right now, surveying his domain. Anybody got the garbage out? Before he moves on. I make a lot of podcasts. Any .NET Rocks listeners? Awesome. Carl's not here. I won't be recording any .NET Rocks this week. I'm going to be doing some run-ads. Carl started .NET Rocks back in 2002, which predates the word podcast by a couple of years. I came on board with show 100 in 2005. We're at 18, we'll do 1830 this week. It's already in the can. A lot of the stuff that I do is based on .NET Rocks. This talk definitely is coming from all these interviews we get to do. We get to talk to really smart people, and so you get to sort of synthesize this sort of vision of what's going on. I do an IT show as well called Run As Radio, and I think episode 863 went up today. And for a brief period between 2011 and 2014, we made a show called The Tablet Show, back when we didn't know what to do about tablets. And now we know tablet development is just development, not a big deal. All right, so we're going to do a little future prediction. So let's refer to Niels Bohr's prediction is very difficult, especially about the future, although I don't know what else you would predict. So let's go through the obvious things that are happening today that are going to shape the way we build software for the next few years. I wrote the first version of this talk in 2019 thinking, what are the 2020s going to be like? And now it's 2023, and it's not exactly what I thought. But did anybody plan for a pandemic in 2019? I don't think so. But obviously the cloud has come to dominate in the past few years. It was less true in 2018, 2019, but today if you don't have a cloud plan, you kind of don't have a plan. Your employer is probably going to ask you, well, how does the cloud fit into this equation? And same for mobile devices. Mobile devices are now the most common computing device in the world. They are the majority of compute. The reason iPhone and Android dominate is just because there's so many of them. We figure there's 4 billion smartphones operating in the world, which pretty much is one for every adult human. And we've transformed society by that. Fundamentally, we are all cyborgs, right? We have digital extensions to ourselves. Now, we tend to, because of science fiction, think about cyborgs as the digital stuff is inside you, but A, yuck, and B, impairs upgrades. But if we don't think of our phone as an extension of ourselves, try losing it for a day. Like, we're pretty agitated when we don't have that device around. It's our communication device. We would just take it for granted that we can talk to anybody anywhere if they'll answer, which they won't, or we at least message them in whatever messaging constraint you currently have. And the Venn diagram of messaging systems is continued to be messy, but that's because it's so all-encompassing. And so we can't talk about future of compute and the kind of work we're going to be doing if we don't include these devices and how they're going to evolve as well. We know how to make an awful lot of data. That's just a byproduct of having a lot of devices feeding into common reservoirs, right? Ultimately, a lot of what's made the modern machine learning models exist is because of this tremendous feed of data that we're generating on the behalf of others. And all of these are obvious trends. More compute, more cloud, more devices, more data. Nothing surprising here. It's all expected. What are the unexpected things? Where are we going to hit limits in the next 10 years? For me, the big one is we are finally going to run Moore's Law to the ground. So Gordon Moore was a person. He was one of the founders of Intel. They were one of the first companies to make microprocessors. Well, actually, they first made RAM. That was their original product. When Intel started up, RAM was still largely core RAM, little ferrous coils wound with copper to store bits. Sounds as reliable as you think it would be. And so the idea of building silicon substrate RAM was a big deal, and that was Intel's original product. And it was while they were making RAM that Gordon Moore observed that for roughly the same amount of cost every 18 to 24 months, we could double the number of circuits on the piece of silicon. Now, they only were able to do that by working very hard at it. Later, that would be called Moore's Law. It's not a law, right? A law is something that happens whether you work hard at it or not. Like gravity. You don't have to do much, gravity's going to apply. But for Moore's Law to be a law, companies work extremely diligently to increase the density of electronics. And it's worked. I pulled this data from Wikipedia. This is a sort of chart of the processor, the density of transistors in processors from the original 4004 in 1970 up till around now. And you see how clean that line is, and that's because we have an exponential number on the left of the number of transistors. If I didn't use an exponent on the left and go up orders of magnitude, we get the hockey stick, the dumb graph, where nothing is meaningful and then it shoots up at the end. It's a bad way to explain this, honestly. I mean, and we're technical people. Getting our heads around an exponential function is hard. When I'm explaining it simpler, I talk about things like this. What is that? Warp drive for the Enterprise? No, that's this. This is a Cray XMP supercomputer, circa 1985. They only made a couple of hundred of these. In 1985, this was the most powerful computer you could buy. They were millions of dollars. They ran on 200 kilowatts of power, so you kind of need to bring your own generator. They're cooled with mineral oil because they're running so hot without mineral oil pumping through it all the time that it will melt. You notice it's kind of curved. They're trying their best to keep the wires as short as possible so that the speed of light doesn't impair the performance of the computer. This is leading edge technology in 1985, and it's knocking out about 1.9 gigaflops per second. So just about 2 billion floating point operations per second in 1985. They modeled nuclear explosions on this. The Voyager missions were computed on computers like this, doing the orbital calculations. Fast forward a few years, say 2011, the iPad 2, about $800. Don't put it in any liquids, that's a mistake. It runs, on its built-in battery for about 20 hours, and it's got about 1.9 gigaflops of processing power. So 26 years later, the most powerful computer in the world is now a device you give to children, and they play Candy Crush on it. That's the advancement of society. And let's face it, that's not fast. That's a 2011 device and a consumer device at that. Today, if you're a consumer and you want a high-performance compute device, you buy a very expensive video card, right? An RTX 4090 these days, if you can find one, they're a couple of grand. They're not cheap, but 16,000 cores in it. Currently pulls down about 82 teraflops at full bore. So 40,000 times faster than the iPad 2. So 11 years later, and this is also 450 watts. So, you can heat the room with it if you like. I hope you bought a big power supply because you're going to need it. And if you want, you can run 2. I don't know why you would. Nobody's mining Bitcoin anymore. That's done. And it's still a consumer device. Today, today the fastest computer in the world, the supercomputers of the world, there's a race going on between the Chinese, the Americans, and the Japanese. And the current leader, literally this past fall, was the Frontier supercomputer in Oak Ridge Labs. So that's in Tennessee in the US. That's based on the HP architecture. So this is a massive multiprocessor machine. And 1,100 petaflops, or 1.1 exaflops, for about $600 million. Needs about 20 megawatts of power, so bring your own nuclear reactor. And takes up about 700 square meters. So clear out the basement. 13,000 times faster than the 4090, or 600 million times faster than the iPad 2 or the Cray XMP. Moore's Law. Right? That's what we're talking about, is our ability to continue to extend compute. And I like that comparison where the Cray's compute power became a consumer device. Are we going to have an exaflop device in our hands? It's possible. I don't know what you'd do with it. But then we didn't know we needed to play Candy Crush in the first place, right? It just emerged that way. And Moore's Law is ending. This graph cannot continue. Why? Why are we running into the limit? Well, we're getting better and better at packing transistors into a smaller and smaller space. And you'll hear these terms like the 10 nanometer process and the 7 nanometer process and the 5 nanometer process. And scientists have built a 1 nanometer transistor, but only one of them. Those are all rough measurements. They're not realistic. Actual circuits are more complicated than that. We have good sensors now. This is an electron tunneling image of the IBM 5 nanometer process. So this is doped silicon layered together. It's hard to measure what we talk about nano things all the time as compute people, the billionth of something. A billionth of a meter is really, really small. People can't understand a billion, right? Same problem as that exponential function. And I always describe this as, if I want to get you to wait for 1,000,000 seconds, 1,000,000 seconds is about 11 days. But 1,000,000,000 seconds is 33 years. So the idea that a nanometer is to a meter as a second is to 33 years. And we're making stuff at that scale today. That's how dense we're getting. This is scanning tunneling microscopy of a silicon substrate. The yellow dots are silicon atoms. The blue holes are phosphorus atoms. We talk about doping silicon when we make integrated circuits so that they change their voltage behavior so that you can apply voltage and pass it through. A semiconductor, this is literally the structure of it. It is a crystal. And when you get down into those nanometer scales, we're running out of atoms. A silicon atom is 111 picometers across, like 0.1 nanometers. So when you start talking about a transistor layered together that's only a couple of dozen nanometers across, it's only hundreds, not even hundreds of atoms. It's tricky, right? Quantum effects start to apply. Like we're just getting as dense as we physically can get, and that's going to be the limit. And not only that we can make these things at all, that we can make billions of transistors on a given die for about $1,000. Right? Keep the prices stay consistent. The manufacturing process has to keep improving without really raising the price so that we'll continue to buy them. And again, we get debate, like how fast did you need to go? And how dense do you need to be? But we've built our entire industry around the fact that we're going to have more compute in about 2 years for the same amount of money. And that ends in the next decade. Now, there's a bunch of things that we're doing or haven't been doing because of Moore's Law. One is we have not really improved architectures for the most part, especially if you're talking about Intel. They've more or less sold the same core chip design for 40 years. Because every time they tried to change it, we got very angry because it wasn't compatible with what we'd done before, and we like compatibility more. And so at this point, the perpetually evolving x64 and x86 architecture has gotten fairly convoluted. The amount of steps involved in a given work cycle, even if it's going at multiple gigahertz, is complex. Now, we do have simpler architectures. The ARM architecture came along quite a few years ago, and it was built for more power efficiency, more compute efficiency. It just didn't have the legacy that the other systems have. But ARM's pretty mature today, and it's one of the reasons you're seeing more and more interest in ARM in general for compute, because the amount of energy necessary for a given unit of work is lower in those architectures. You can expect, as we lose the ability to get more compute for free by buying the next generation processor, that optimizations in architecture become much more important. Now, for us as programmers, for the large part, we're insulated from that. Our modern programming environment almost completely abstracts us from the actual underlying hardware. If you're living in .NET land, it's Microsoft's responsibility to make sure that the common language runtime compiles and optimizes to the processor you have. They do that all of the time. We don't even think that it happens. It's kind of magic. It just works. In that brief period where they thought ARM was a really good idea, now that they're coming back to that idea again, you could compile .NET to ARM. It went away. It'll be back because it's nothing that we have to do. It's their responsibility to do implementations against the hardware. That's the power of abstraction for us. I would argue that today the M1 and the M2 made by Apple are the most advanced processors out there architecturally. They're ARM-based, but they've also condensed a lot of things. Most of the memory is here. They have tensor compute units, or basically units optimized to do neural net calculations. They have the GPU integrated in, putting all those things in a single die, putting 40 billion transistors together, all working and playing happily, has some benefits. And so, those are some of the nicest computers we can buy today, and it sort of speaks to what the future looks like. And I'm an advocate of William Gibson, the guy who coined the term cyberspace while typing it on a Wedgwood typewriter. But his quote is, "The future is here, it's just not evenly distributed." So if you want to understand the future, one of the easy ways to go is go look at where the concentrations of real rare innovation are, and what's happening in Cupertino with processors like this is pretty profound. It speaks to what phones should look like in the future and what our other compute devices can be. Deeply integrated circuits. The modern manufacturing foundry allows us to build very customized circuits that are as close together as possible, to run as fast as possible with the least amount of heat and the least amount of battery waste. All right, let's stop talking about the underlying hardware. The real constraint these days is the network. 5G was wonderful. It was heavily advertised a few years ago. Now it's here, and nobody can tell. Works perfect. It's a good question. In theory, these standards for wireless are about increasing frequency to densify more data so more people can communicate simultaneously. The downside is as you move up in spectrum, you decrease the penetration. So our old 2G phones, which were living down in the 900 megahertz range, worked beautifully in basements. When we got up to 3G and 4G phones and we moved up into the 2 gigahertz band range, we had trouble communicating into enclosed areas. Right? Some buildings worked, some not so much. It was easy to get into a Faraday cage where your phone wouldn't work. 5G bumps this up into the 20 gigahertz range. Big increase in data density, but the penetration goes down a fair bit. It's blocked by things like trees, bodies. I've stood in front of a 5G tower doing a speed test with my phone and going, wow, that's smoking fast. And then I turned around. And 20 gigahertz apparently doesn't go through me. So there's challenges for these higher frequencies. There is a 6G specification underway, but there's no simple solutions here. Network is going to be our constraining resource as developers. We have to think hard about how we move data between points of compute. That's always going to be a limitation. There are no workarounds largely for the laws of physics. The speed of light, that's a law. The satellite networks that are going up now are very interesting for certain applications. What we've really reached is a point where much of the parts of the globe that don't have good cellular coverage can have sufficient satellite coverage. So more and more we're reinforcing Esther Dyson's belief that it was easier to put networking everywhere than it was to build a good disconnected client. So you just presume we're going to have bandwidth everywhere. I got on the early Starlink beta because I have a place sort of up in the wilderness in BC where the bears are even more common, and it's impressive. Like that's just a pizza box size antenna. You need a clear shot of the sky. That's the hard part. And if you've got a clear shot of the sky, you've got about 400 megabits down and 100 up at 20 milliseconds. You can game from there. It's not as fast as your synchronous fiber, but it's faster than you would get in most isolated areas. So that ubiquitous connectivity and huge amounts of compute available in very small devices, the other side of Moore's law is the old hardware gets very cheap. And so we're seeing in things like automobiles where they won't spend money on compute, they still have it. They're now starting to put 3G cell services into all cars so that all cars have telemetry back to the factory whether you want it or not. Because it's more important for the factory to know about how you're using the car. So this model of ubiquitous computing is emerging more and more, where every device has an IP address and can connect to the network and is communicating, perhaps not for your benefit, but for the vendor's benefit, but it's always communicating, and we have options there. And we're going to be responsible for a lot of it. I'd be remiss in just setting the stage for all this to not talk a little bit about the pandemic. When I wrote the original version, it wasn't a thing, but we've continued to deal with this. It's obviously in the later stages. Our friend Satya Nadella was famously quoted by May of 2020 saying, 2 years of cloud migration happened in 2 months. as everyone discovered, yes, you can work at home, and we tore apart our perimeter networks and expanded our VPNs and quickly shuffled whatever we could into the cloud. We changed the landscape of work. We changed the landscape of compute. I mean, for most of us in our industry, working from home was just not a big deal. We've been doing it anyway. I do hope one day to make either a video series or a talk just on how video conferencing evolved over those 2 years. Remember that period where everybody thought all of those inlaid graphics with the hats and the horns and things was a good idea? It lasted like 3 months. For 3 months, everybody had fun with that, and they were like, okay, that's really dumb. And they turned that off. But that's the evolution of etiquette and perception. And today, it's really interesting to see how everybody comes on with a face initially, says hi, and then when somebody actually starts to talk, most cameras go off to not distract. We're developing an etiquette for that model. We were rushed to do it. But we're also seeing the other side of the pandemic. We're starting to see the economic impacts. The side effect of mass layoffs was a loss of expertise, that in general, all work chains are less efficient today. As we tried to gear them back up, and you have a 20 or 30 or 40% inexperienced worker role across those chains of work, you have a lot more mistakes, and they cascade on top of each other. We had the supply chain deeply disrupted, ports that had too many empty containers and not enough full ones, not enough space to move things around, and literally going to take years to straighten it out. And then the byproduct of all of that friction in supply was an increase in demand for certain goods, which then got interpreted as inflation, and here we are, it's 2023. I hope you're having fun. Now, what does this mean for us in our industry specifically? Because for the most part, we've had 20 years as developers just in a growth mindset. 2008, 2009 notwithstanding the sort of Great Recession, because I think for the most part, technical industry was insulated from that. We were not as impacted as much as many others. So I've talked to folks that have been working since after the dot-com bust, 2001, 2002, and it's just been build what you want, go faster, build more, explore great ideas. Now, I'm older than that. I started writing code in the 80s when economics were a lot tougher, and we focused really hard on this concept of return on investment. The problem is that when we're software developers, we rarely are directly responsible for making money for the company. Typically, the things that we make are tools that allow those that make money for the company to work more efficiently. If the things we're making don't do that, they're really not that important. This capitalist model has always functioned on the idea of rapid, relatively inefficient growth, followed by a period of sort of cleanup, shaking out the weak stuff, a bit of a recessionary period for a year or so. We cut the sort of fat off, and then we'll grow again. Except that we've gotten good enough with our economic models to avoid that whole cleanup phase for 20 years. And now that we're looking at one in a very serious way, and folks are seeing what it's like to have a 5 or 6% interest rate, and the new costs of things, the pressure on energy and so forth, companies are being more reflective. They're sort of looking back and going, are we doing the right things? Are we focused on the important stuff? And it's in our best interests, with our skills and domain knowledge in the companies that we're working in, make sure you know how your company makes money. Make sure the things you're building help that. Because we are productivity amplifiers. We're incredibly good at building tools that allow the rest to work faster, to do more. We can help companies survive in difficult times if we work on the right things. All right, we wanted to talk about technology. We've kind of set the stage. Here is the landscape we live in today. So now that we know we're living in a cloud, and we're living in a cloud world, mostly smartphones, we're not going to count on new compute going much faster, and in general, our employers and our customers are going to be tighter with their cash. What should we do? Start with the browser market, because the browser market is kind of stable now. If you really want to use up a lot of memory in your computer, there's Chrome. If you want to be frustrated with how well your websites work, you have Safari. If you want to use a browser nobody else cares about, there's Edge. And if you want to be an angry anarchist, there's Firefox. Like, you have choices, right? There's no perfect solution to any of these. Nobody's utterly dominating the market. I mean, Chrome is still a big player, especially for your typical employer. That's likely the browser you're using. You tend to build to that. And we're clearly seeing the rough edges where not all the same things work together. But we have the tooling sets. And on .NET Rocks, we made fun of the rapid rates, like, hey, we've got an hour-long show here. There'll be at least 2 more frameworks before this is done. I feel like that pace has eased off a little. I think people want a certain level of stability. Angular is not the new sexy anymore, but its utilization level inside of larger companies is massive. And those top 3 across the board seem to be the majority of web development. And we're still doing mostly browser development, especially for companies, because it solves a deployment issue. And they're always running latest version. And that's things we want from that, even if we have to constrain the feature set somewhat. And all of these libraries have, to some degree, advantages for working in the heterogeneous client world that we have, that people are expected to be able to use those pages on a phone and on a tablet and on a PC and have a reasonable experience on all of them. It's still not easy. Development for us the easiest time of development was when the device you were writing the code on was the device it would normally run on. That just hasn't been true for 20 years, whether we acknowledged it or not. Now we typically are writing on a desktop PC or a robust laptop, but we're running it on smaller form factor devices. And that's a way more difficult thing to develop for. It's a more complicated model, it's a longer cycle. But if you're not respecting that cycle, you struggle with what you're making. The progressive web app movement has helped us, at the minimum, to give us an icon for regular users to be able to get to that web page, because goodness knows they couldn't figure bookmarks out. Right? So now we have an icon, it starts up a frameless browser, that's good enough. There's a bunch of other great stuff in PWA, and the 3 guys who use it think it's great. And then there's our friend Steve Sanderson, who brought us WebAssembly in the form of what would eventually be known as Blazor. Now, he didn't invent it, he wasn't first, but he definitely brought it for us in the .NET community back in 2016 at the NDC conference in Oslo. He showed it off for the first time with a very bizarro version of C# that allowed us to run C# on the browser. And really what WebAssembly has evolved into is a kind of container strategy where the inside surface of the container is this browser environment, a sandbox that's relatively safe to operate within, and you can introduce almost any kind of code. Microsoft took their time committing to Blazor. Microsoft doesn't like being first, it seems, these days. They kind of sat on that project as an experimental project until Golang for WebWA shipped. As soon as that happened, well, then Blazor came out. But it was like, nobody wants to attack JavaScript, but we do want to program in the languages we want to program in the devices we want to program in. And WA gives us this ability to program in the languages of choice down on the client device, still in the browser. So I still have my deployment issues solved. I still have continuous update models where every time you click on it, you get the latest version. Like all of the benefits of working in web development, but now I get the language that I want to use. And if you've listened to the show, we've been talking about other places that this container could run. I mean, Blazor made it absolutely obvious to us that we can run it on the server, we can run it on the client. But now it's interesting to start thinking about different points of compute. I don't want this code to necessarily run on the client device, but I want it to run close to the client. So could I define a set of parameters for where this block of code could execute that it could run in a CDN, an edge point of some kind? And this is all experimental, but I'm hearing it more and more often that the WebAssembly is another kind of container, and what the potential of that offers to us long term. So if you haven't explored this world and sort of poke around what's possible there, just understand this is an area of growth. Extremely smart people are looking at where they can take WebAssembly to. Now, if you want dumber areas, we could talk about Web3. It's easy to make fun of, mostly because it's pretty silly. I see it coming down to 3 central ideas. Decentralized web is, I think, the most reasonable aspect of Web3. If you think about Web 1, late 90s, early aughts, the whole .com boom, not .com from Microsoft's perspective, but the idea of the internet becoming a popular thing, that was very decentralized. People ran web servers on machines under their desks, connected to the internet. It wasn't a good idea, but it's something we did. And it was powerful and flexible, except it just wasn't reliable. Right? Sometimes that machine, sometimes you trip over the power cord. Sometimes the cat barfs into the CD drive, right? Like stuff happens, and that machine was actually on the internet. Web 2 was far more centralized, right? We gave up our ownership of those devices on the internet for a service provider. It's just that we chose folks like Facebook. But you can still put GeoCities in that can as well if you want. But now we're getting into more interesting compute models with distributed execution. And the problem, of course, is that those products turned into other kinds of exploitation of us and us not controlling the value we're actually making, and now everyone's a little bit sick of it. And so decentralized web is becoming hip again, just trying to do it in a better way. Running on the cloud, you could still be largely decentralized because it's all about ownership of data. So can you run your own services through a provider who's not really running competing services directly, but rather having other people compete in that space? I look more to stuff like the Shopify model, where there's no reason for you to employ your own e-commerce engine anymore when you can go to a Shopify and run their engine for a set fee with many thousands of other people running the same engine for their products. But the one person not running an e-commerce engine is Shopify themselves, right? They're not a competitor in your own space. That's fairly decentralized. I can live with that. The silly parts when we get into Web 3, blockchain's not inherently stupid. It's just wildly misapplied, right? The idea of a distributed data engine is pretty compelling. It's just that people don't think about it well. When I have a customer asking me about, well, we got to use blockchain, it's like, why? Because he saw it in a magazine. Like, what do you want from it? What's the difference? And often with most companies, they still want to be central point of control. It's like, so you don't want blockchain. The idea that other entities can introduce transactions into this data independent of you is the basic stepping point. Like, if you're not going to do that, then what are you talking about? Why do you need this? But blockchain's got the problem that BitTorrent has. BitTorrent's problem was that it came out of Napster, out of stealing music. It was a good protocol used where its initial use was a nefarious use that was ultimately illegal. And blockchain has the same problem. It's bound to crypto. And as we're seeing pretty clearly these days, crypto is pretty much a Ponzi scheme. And so are we going to get something from it eventually? Maybe. Are most people just going to lose their money? It sure seems like it. It's easier to see that now than we saw it before. But that's the part that's really contaminating Web 3 is these fairly good ideas bound up with an idea that was very easy to exploit to fairly destructive purposes. And so I think most of us these days who are a little more serious about stuff are going, I think I'm just going to stay back from that rodeo and let it wind down, and then we'll see what pieces are left in the end. Web 2 didn't happen overnight either. This exploration of new ways to use the internet, it is an exploration. It takes time. There's no other way to do it. And so it's a question of, are you going to jump in and be part of that exploration, or are you going to witness it and then make your move later on? If you think like an engineer, you're pretty conservative, and you're not the first. You're big on the IT mantra of change is good. You go first. Not a bad way to look at crypto these days. .NET's in a good place. Goodness knows I'm glad about that. I make a podcast called .NET Rocks. And back in 2011, we thought maybe .NET doesn't rock, and things were pretty hard. But 11 years on, 12 years on, .NET's rocking pretty hard. They've done a remarkable thing. They've rewritten the entire thing to be a cloud-centric, heterogeneous client platform with some limitations without having to replace all the tooling in the process. I mean, if you learned how to develop against .NET in 2010 with Studio 2010, I can drop you onto Studio 2022 and .NET Core, and you won't be confused. You'll more or less get it. There's a bunch of new stuff, and there's some edges to things, and we focus on some other elements. But really, we've had a complete overhaul of this 20-year-old stack over the past 6, 7 years, and yet we don't have to relearn. We don't have to start over. We get to move most of our code onto it, and the new things we write, we use familiar skills. If anything, the biggest problem Microsoft has right now with this is that it's so similar, we still have our old practices. We're not using the new language features. We're not taking advantage of the new stuff that's been brought to it. And the only way they're going to fix that is tooling. Because compatibility is so important, they're not going to take stuff away. If you're using C# 2 constructs, they're going to keep working. but you probably want to use a new one. So I think you're going to start having more Clippy events where it pops and goes, wow, you're coding like it's 2007. Can I help you? Because you need help. And the big new tool in this space is Maui. So this is the culmination of a tremendous effort inside of Microsoft to consolidate a client development solution that deals with the heterogeneous client and multiple platforms. It's still pretty raw. Again, the conservative engineering type will look at that and go, you know, I'll let you guys iterate on that a couple of times. You kind of get it right at the third version. You're kind of like at a version and a half right now. So we'll give you a little more time. But the goal is challenging. The idea of this magical, unified client development model that works for all the devices. Something we want. Our customers couldn't care less about. The customer only cares that it runs on their device. They don't care if it runs on anybody else's device. We're the ones who want to write one code base that runs on all of those devices, because otherwise we can't keep them in sync, or we're leaving somebody out and they're angry with us, and that's never fun. So this is Microsoft's client-side attempt on this. And I mean, I'm excited for them. The 7 version is substantially better. I think this will be almost sexy by November of this year with .NET 8. It just takes time for them to get this many features and this many teams cooperating across the stacks. And if you're sticking with web development, I don't blame you, because it solves this problem with its own set of limitations. I've yet to see a Maui implementation of a cross-platform client solution where I said, wow, you couldn't do that with web. We're not there yet. We might be. I don't know the answer to that. We've talked about this a few times on the show, and it doesn't seem to be going away, the Power Platform. So here's the other reality, is that we kind of know what the client landscape looks like. We know there's phones and tablets and PCs. An awful lot of our data over forms problem space in work is all dependent on the cloud tenant that our employer has anyway. And so the fact that we can essentially run this set of tools that builds a bulk of that for us is pretty compelling. But even more importantly, these tools are straightforward enough that a domain expert can take a pretty good shot at an 80% solution for a workflow for a company, and then it needs to be cleaned up by someone with a bit more experience. But a lot of UX development can be done by the person who's going to use it. Now, this has happened before. This is Access and Visual Basic in the middle 90s, where most people who grabbed those tools were domain experts, not developers. They became developers later, and I think we're seeing another wave of this. But the parts that we find the least pleasant as professional developers, that UI, multi-platform UI problem, this thing kind of knocks out. And then it has a set of hooks back to back-end services with some limitations. They're all customizable. We as professional developers can build additional endpoints for the Power Platform. And if you're good at the UX side, you can build custom components on the UX side for these domain experts to use too. But I'm looking at our to-do list, and we're not getting to the bottom of it. So if there's a group of people out there that want to move things along by taking on some of that work, do it. The way Microsoft's licensed the thing, it's for internal apps only. You pretty much cannot put a Power App into public. It has to be authenticated members of the tenant. So it's for internal apps. They weren't fun to build in the first place. So anything we can do to get more of those off the table and modernize them, right? You're looking at that web forms app that the CIO wants to run on their iPad. And suddenly the fact that a Power Platform could get you a prototype of that in pretty short order, it's pretty compelling. I've mentioned WA in the context of containerization. Containerization is an ongoing, evolving thing. It's only getting bigger. I got a recent show up where we were talking about Azure application identities. And that ties into giving a security context to an application that's going to run in the cloud. In a lot of ways, containers do that too, right? We're demanding a manifest saying, this is what the app, this is the resources the app needs, this is the operating context it needs to operate in, here are the rights that it needs, the access points that it needs, and more importantly, if it tries to do anything that isn't in that, kill it. Containers are just the evolution of that. In the next few years, I think we're going to see containerization of software in general on desktop machines because of the security problems. that when a given piece of software gets exploited and it tries to do anything outside of its normal set of behaviors, the operating system recognizes that it's exceeding its container limits and stops it. Now, that was always a good idea, and Microsoft's tried to implement this in a few different ways for a long time, but I think the security context is going to win. I look at what's happened in cyber insurance in the past couple of years. Today, if you want to get cyber insurance, not only is it more expensive, but even they require multi-factor authentication. But more and more, I'm seeing things like you're required to do a privileged access audit. I wouldn't surprise me at all if the insurers at some point say, if your apps aren't running containers, you're not insured, because they see them as ways to avoid the exploits that the black hats are using. So that might be what pushes this technology over the top, is it becomes a consistent industry-wide way to resist the ransomware and other security attacks. And if you're feeling a little overwhelmed with all the stuff I'm rattling through, because I get to just tell stories for a living, I don't have to implement any of it, which is why it's all easy for me, that's okay. There are a bunch of ways to have a great development career. Staying on the leading edge is really fun, if it's fun for you. You know, the downside to the leading edge is also the bleeding edge, and sometimes you bleed. You can also have a great career, and many people do, by becoming an expert in a stack that your company values and staying that expert. It may not be the newest technology anymore, but it's the one the company relies on. And they need those experts. And they need you to continue to grow and to be good at that technology and to keep it functional for the organization, to keep doing the things it needs to. Don't jump because the thing is new. You jump because it can no longer solve the business problems that it needs to solve. I've talked to folks that started doing web forms development in 2005, and their company still uses a ton of it. And it works. It's reliable. It's a known set of problem spaces. They have they're 15 years into this or plus, and do I really need to jump to a new stack? It's like, no, those apps aren't going away. And in fact, even when they are, they're going to technologies that are orthogonal to web forms anyway. That's why Blazor got so hip. If you're a web forms developer and you look at Blazor, you're just not that surprised. This looks like something you've done. It's not that hard to jump onto the new stack. So the question is, what did you want to do? Do you want to be part of the group of folks that are always learning and pushing on a new thing? Or are you going to be the expert in a given set? You find a space that you like and you stay in that space and you get really good at that space. And now you're an expert in a diminishing pool. Like, your pay's still going to be good, but you need to maintain your expertise. You need to keep figuring out where the limits are and what's possible. Like, it doesn't mean you ever stop learning. We don't get to do that in this industry. But it's a question of what you focus on. Do you really want to learn the new bits where we're all just trying to figure it out, or you continue to expand on the space that you're in? There's not one way to do a great career. Let's talk about artificial intelligence. And I use this image for the simple reason that it is the reason that we think about AI the way we think about it. It's a terrible term. It was coined in the 1950s by a guy named Marvin Minsky when he's trying to sell stuff to the US military. The first time regular humans heard the phrase artificial intelligence, it was in the movie 2001: A Space Odyssey, and HAL, and then he tried to kill everybody and set up our relationship with artificial intelligence going forward. It's an umbrella term. The one thing I know for sure about artificial intelligence is as long as somebody's calling something artificial intelligence, it's because it doesn't work. As soon as it does work, it gets a new name, right? It becomes deep learning or predictive analytics or speech-to-text systems. As long as it doesn't work, it's AI. And so when folks talk to me about, hey, I'm working on this AI problem, it's like, what are you really working on? Like, is it a machine learning model? That's the new thing, right? Like, really, what really came out of Jeff Hinton's papers in 2011 that led to stuff like Siri and all the voice recognition and ultimately these vision interpretation models is all deep learning models based on machine learning, right? And this particular graphic I like because the short lines are the oldest technologies. Those planning, scheduling, optimization, those are back in the 50s. Expert systems in robotics from the 1970s. Original speech recognition systems go back to the 80s. And then in the 2010s, we get this current crop of image recognition, vision systems, language interpretation. And we can incorporate that into our software today. There are good libraries. You don't have to invent stuff. It isn't research anymore. You want an image recognition module? It's a module. You load it into your software, you have an image to be recognized, and it can recognize it. This is a real thing. The software was doing what you told it to do. It said, oh, no, 3 dogs. And you've run into the chatbots, right? They're out there. They are first-line tech support for almost everything today. You're going to get a chatbot voice, and sometimes they're speech bots. And they are getting better. That doesn't mean they're good. We all learned to say agent very early on if we want to get out of that loop. These are, again, tooling sets that we can work with. The area that I'm really fascinated by right now that Microsoft's working on are these form recognizers. So the idea that I can use an image recognition system to look at a form and it recognizes what is form and what is data, and then associates the two together into value pairs. That's pretty cool, right? That we have a different strategy to digitizing a form rather than building it by hand in code. Now the tool would actually recognize it for you and generate it for you. This was really about using initially paper, because they call it a form recognizer. Like, can I parse a page and have it pull the data out of it? But I immediately thought, hey, aim that at a web forms page and read and parse it for me and make it into Power Platform stuff. Like, could I just have a tool thumb through all of the different views in an application and regenerate it in a new language? Why not? We have machine learning models that are capable of parsing the data. The final area in the machine learning space is that it's gotten powerful, actually has been powerful for a while. And when people are asking about, hey, my kid's getting into technology, like where's the big career opportunity? It's analyzing data. We have more data than ever before. We're analyzing it less and less effectively because we're just outnumbered. There's so much data and only so much time. The good news is the cloud is making things simpler for us. In the 90s, we had most of these predictive analytic models. It's just that each one of them represented a huge amount of compute. And so you'd do a bunch of pre-work to figure out what the most likely analytic model would be effective on this given data, and then you'd build out a system and run it once. And it would take weeks. Today, this is a couple of hours in Azure. Load the data, you'll spend more time loading the data up. Then you'll run all of the predictive analytic models, and then you'll run model analysis against the models to figure out the one that fits the data set best for $20 worth of compute. So we have better tools than ever for doing advanced analytics. And as we go, and when we talk about advanced analytics, the predictive model is really what's the next number that's going to come from this, what's the trend on these, is this going up, is this going down, right? And we have plenty of tools in those sorts of forms. As we start adding in machine learning, we do it in bulk. We're able to do more of them faster and compare them so that we can select models more efficiently. It's less time on your space and more just hammering it with compute. But you can go to a more advanced stage. Given you take a predictive model and it says this is the most likely outcome, now you can actually run a scenario beyond that. You're getting into prescriptive analytics. So you're cycling the predictive model with actions. You've been experienced this is where you know it or not. Have you lately thrown a bunch of stuff in a shopping cart and abandoned it, and then you get an email from someone saying, hey, you put this stuff in your cart. Like, can I give you 10% off so you'll go buy it? You're seeing a prescriptive model saying, how often do I tickle this person now that they've shown some interest to increase the likelihood of completing a sale? There's no humans involved. It's all software. But they're now running these prescriptive explorers to say, how often should I hit them? Given 1,000 people did that, and I emailed them this way, what was the response rate? What if I email them this way? What's the response rate? That's automated now. That is prescriptive analytic models. Now, obviously, in the e-commerce sale, there's one side, but you're also seeing the same models used for things like, when should you evacuate a town for a forest fire? If I wait till it's obvious that the fire is going to hit the town, now I risk people's health in the crisis of trying to get them out. Or is it better at a low stress level to say, let's move them early, it'll cost us less, the chance of them being injured or killed is lower, and then if the fire goes the other way, it's not that big of a deal, right? We're still building prescriptive models to explore the psychological effects of emergencies and being able to act more effectively to protect people. We can also make video games. So this is one of the OpenAI models in the early days where you would describe a game. This is someone making a bad version of Asteroids, and it would spit out code for you. This is not that exciting anymore. Most people have played, hopefully, with Copilot now, a whole other way to pull up code you don't understand. You used to have to use Stack Overflow for this, but now you can to a machine learning model, so there's fewer people saying that's a dumb question. I'm concerned with the training set. We've done a couple of great shows around this with folks like Michelle Manning, where we, maybe generating code that works but isn't secure or isn't, reliable. They've trained it against all of the open libraries on GitHub, and that means it's only as good as the code that we put into GitHub. Some of the code I put into GitHub I'm not proud of. So it is interesting to say, how can they improve this to say, hey, I only want highly secure code that's thoughtful of all of those kinds of things. They're now starting to stick language onto this. So now you're going to talk about what code you want to write. And the VP of the Power Platform, Charles Lamanna, announced they've made a version of Copilot for Power Platform. So, you had a no-code solution where you're drag-and-dropping the form? Too much work. Just say, make me a form. Right? Now use the image recognizer, show them a copy of the paper version of the form, and it comes up. So those are machine learning models for programming. They are tools for us to use. The whole, we will all be replaced by this is silly. It always was silly. It's only getting sillier the longer we use these things. But if you don't use them in your routine work, you're kind of missing out. It's an accelerant. There's no excuse for not understanding the code you're putting in your system. So the idea that this is you were using Google, sometimes you're using Stack Overflow. Why wouldn't you use Copilot to pull up code and then evaluate that code? It's easier than a blank screen. It's anything we can do to get ourselves moving on a given problem space. But it's still our discrimination. The tool does not know that this code is right. All it knows is it fit the criteria you described to it at the time. That's as much as it knows, with some percentage of probability, hopefully in the high 90s, but not always. And ChatGPT, about the same thing, right there. I call it a Dunning-Kruger accelerator. If you know nothing about a topic, ChatGPT is awesome. As soon as you know something about a topic and ask ChatGPT, it's not that awesome. Not actually concerned with facts. What replaces the smartphone? I mean, the smartphone is dominated. It's now the primary compute device, but it's kind of mature. The phones get bigger, they get smaller, they have 1 camera, 2 cameras, 3 cameras, way too many cameras. But they're kind of the same. They're a slab of black glass. We're kind of ripe for disintermediation. The obvious device is some kind of AR headset, right? It's some pair of glasses that we can put on that puts the data directly to our eyes. It does everything the phone does without having to pull it out, right? And actually gives us a bunch of other capabilities because now we have instrumentation on our head so that it can observe the world around us because we're not paying attention. And that offers a bunch of possibilities. That being said, 2023, not a good year for AR. Apple's just announced. This is a mock-up of what we thought Apple was going to make. It's all a lie. And currently, Apple says they're not making anything. They've backed off. So whatever prototypes they were working on internally, they're not happy with them right now. There are commercial products that are glasses with devices on it. This is a Qualcomm device called the XR1. You can buy this today. It's about $1,000. It's tethered to an Android phone. Right? It's just a USB headset that has microphones and speakers and cameras and screens integrated into it. And you're seeing these used in certain commercial applications. If you want to look more like Google Glass, you can do this with the Toshiba devices. This is the Dyna Edge. So I want one eye, a little more industrial looking. Okay, this hardware exists. There is HoloLens, but HoloLens is not in a good place. This is the Trimble version of HoloLens 2. This is the one they wanted to put on all construction workers, because construction workers are good with equipment, at $3,000 a piece, plus about $1,000 a month in operating costs. When we started doing some case studies on applied HoloLens products, I was stunned at how much Azure it eats to operate it properly. Now, for certain markets, that makes perfect sense. Construction side, not so much. But if you've been paying attention to the recent round of layoffs, you know they've pretty much laid off the entire HoloLens team. The leader of the HoloLens team, a guy named Alex Kipman, left Microsoft back in July. So they've been a little bit leaderless for the past few years. And then the Army announced they were going to shut down a project. They want to do more research on it. And then this round of layoffs came. So it looks like the HoloLens is an orphan for the moment. I mean, the opportunity in certain verticals is really interesting. The industrial applications where basically equipment becomes transparent, checklists are live, you're making continuous video record of the maintenance that you're doing. These are all interesting applied cases. I looked at this very much as the that the AR glasses were in the same place that the BlackBerry phone was in like the 1990s. In the 90s, if you wanted email on your phone, I know, crazy, you had to buy these $1,000 phones in the 90s from RIM, called the BlackBerry, and it had a little keyboard on it, and you had to run a custom version of Exchange Server inside of your organization to make it work. So you need a couple of guys in lab coats and a whole ton of licenses, and you too could have email on your phone. And it was so popular in the 90s, they called them crackberries. But it needed to be the right vertical. That cost had to be worthwhile. That continuous access to that person was important enough, right? You saw it on like the West Wing, right? The politicians and bureaucrats needed this sort of thing. And of course, today email has been completely commercialized. It's in every device. It's not a big deal. But I look at HoloLens and the AR devices that way. For the right vertical, where you can afford that spend is trivial to its value, totally makes sense. Consumer device? No, not there yet. And we don't know when we will be. It's an insanely complex device. Now, the HoloLens 2 is 6 years old. We never saw the HoloLens 3. So the tick-tock of Moore's Law still applying, we should be able to make a dramatically better headset. We're just struggling for the applications for it. I'll make fun of Meta very briefly. It's not hard to do anymore. It was funnier a couple of years ago. We would have said, hey, Zuckerberg created the largest loss of value in all time. He burned through $10 billion in a year. But then, I mean, Facebook was a $1 trillion company. Now it's a $300 billion company. Well done. But then, let's look at Twitter or Tesla. Like, billionaires messing up their companies seems to be a style. I presume it will pass. These headsets are compelling. This was really John Carmack, the guy behind Oculus that got acquired by Facebook, who has now put down his laptop and go, okay, I've had enough of you people, and he's left now too. So any sense that Facebook's along between Sheryl Sandberg leaving and Carmack leaving, Zuck's by himself, and I think fairly far off the rails. Microsoft seemed to be playing ball. They wanted the Teams version of this with the Quest Pro, the $1,500 headset in the Horizon workspace. They've now backed away from this. So this is kind of a dark time in general. We're kind of for AR and VR. If you are interested in developing in this space, the obvious tool is Unity. The bulk of development being done in this space is done in Unity. It's C# centric. It's its own custom build, essentially. If you've never played with this, it's an experience. And I recommend the tool often to kids who think they want to make games. Because you can watch a few videos, use the free version of Unity, and you can do a lot. You can make a pretty straightforward side scroll and have an experience, and then start to think more profoundly about the challenges of writing games. But what Unity has going for it is a really good set of 3D libraries for making it easy to do all of that three-dimensional work. Okay, one last topic, and then we'll wrap up. Quantum computing, because people love it. So quantum computing is a kind of supercomputing. It's not likely to be a regular general purpose compute. It's for supercompute problems. So the same way that we build these titanic supercomputers for modeling weather and things, these are the kinds of problem spaces that quantum computers are good at. There are a number of companies that are building a variety of different styles of quantum computers. This, to me, likens very much to the late 40s, early 50s in general computing, before the development of silicon. So every computer is kind of bespoke. This is the Sycamore computer built by Google. It has 54 qubits. It was the first to achieve quantum supremacy, where it worked on a particular problem that was considered thousands of years of compute in traditional computing. That's questionable. My favorite part of that story was it's a 54-bit quantum computer, except one of the bits was broken on performance day, so it was a 53-qubit run. This particular design of quantum computers is what they call transmon quantum processing. So this is a way of doing quantum entanglement with ultra-cooled material. They cool it in liquid helium, which is dangerous. The Chinese have a photonic quantum computer that they had up and running in about 2020 with 113 entangled qubits. They did a boson sampling compute in 200 seconds that would have been multi-billion years of traditional compute. it was a known problem. It's kind of a proof point. But again, these are getting there. And then IBM's Eagle and Osprey and Condor architectures in the 100 to 120 or so qubits. That one was in benchmarking in late 2021, 2022. We haven't seen the results from it yet. They were promising by last year to have a 400 qubit processor. That hasn't materialized yet. And this was supposed to be the year they produced 1,000 qubits. That hasn't happened either. But the real question is, what the hell are you going to do with this thing? Like, the only other thing you ever hear on the news is the end of security, that we're going to be able to break RSA encryption, which is true, kinda. In the end, encryption strategies that use these very large prime numbers are susceptible to the compute strengths of quantum computer. If you have 4,000 or 5,000 entangled qubits, you should be able to crush through 128-digit primes in a matter of seconds. We don't have to use prime-based encryption. There are other kinds of encryption, in fact, and the NSA is currently recommending that we switch to lattice-based encryption. It's just not as efficient to encrypt with other kinds of encryption strategies. It turns out the computers are good at prime numbers, and it's a cost-effective way to do encryption as well as decryption. So forget the encryption problem. Solvable, not interesting. The most interesting problems in the quantum computing space are actually chemistry problems. And the classic one for me is in agriculture. So in the pre-technological era, if you wanted to grow crops routinely, if you were planting wheat, if you kept growing wheat in the same chunk of land year over year, you got less and less wheat because you depleted the soil. You had to rejuvenate the soil. Now, today, in an industrial world, we have the Haber-Bosch process where we make industrial fertilizers. And after you have a season of growing wheat, you then fertilize the snot out of that land and replenish the soil to grow wheat again. But before we had that, we rotated crops. And there are bean plants, typically, that has a rhizome on it that lives on the roots, and inside of that is an enzyme called nitrogenase. And nitrogenase naturally affixes nitrogen. It takes water and nitrogen from the air, and in a catalytic reaction, turns it into ammonia. So in the normal crop rotation, you would grow a crop of beans, you would harvest the beans, you'd plow the plants under, and then you'd let the land go fallow for a year. You'd let those roots rot, and they would release fertilizers back into the soil. And then the third year, you can plant wheat again. That's the traditional, non-technical way to do it. Chemical fertilizers avoided that, but chemical fertilizers have their own cost. Right? They're about 1% of the energy consumption of this planet is based on making and distributing fertilizers. So if we could utilize this thing that a bean plant could do, we could have a significant impact on agriculture. The problem is that the catalytic reaction that goes on inside of that enzyme involves atoms of molybdenum and iron. And it's a 2 to the 170th complex problem to understand the electron interaction, which is like more atoms than are on the Earth. A mid-sized quantum computer, something in the 400 qubit range, should be able to solve this, should give us an example of the correct catalytic reaction. That doesn't mean we'll immediately be able to implement it, but once you know what the reaction looks like, you have a chance of now engineering an implementation of it so that we could be making fertilizer directly from air at low power, plant power, and be able to grow food more routinely. It's an interesting quantum problem. There are other quantum chemistry problems like that. Battery design is largely based on experimentation, not on our actual understanding of the interactions of the compounds. What we have done in battery development today is gotten really good at iterating on trying different combinations, not actually understanding the optimal combination. It's a quantum computing problem. Modern superconductors, the Rebco superconductors, which are made from rare earth materials and barium cupric oxide, are ceramics that are superconductive at liquid nitrogen temperatures, as opposed to niobium-10, which is superconducting at helium temperatures, which is way harder to deal with. We've had these superconductors for about 40 years. We just don't really understand how they work. And so it's hard to make better ones. And again, quantum chemistry problem. These are all deterministic problems. So the real question is, how many quantum computers do we need? Because once you've solved it, you kind of don't need to solve it again, right? It's not a non-deterministic problem where you need to do it every time, like a weather problem. It's just a deterministic problem. And it reminds me of of Thomas Watson's statement when they were first building mechanical mainframes for the original version of IBM, where he told his board, I think there's only a market for like 5 of these, and then they went out selling and they sold like 25, and it was a revelation. But that was because back then the computer looked like this, right? This is before Intel. This is before the silicon transistor. If your computer looks like this, you can't envision a smartphone. Like, you can't see it from there. It's too hard. The first transistor ever made in Bell Labs, the germanium transistor, looked like this. It's pretty hard to look at that and make M1 chip. Right? It's a big jump. So going back to that mainframe, what made traditional computing useful was the integrated circuit. We suddenly had a stable, reliable way to make bits. We made RAM, and then we made processors for them. They were consistent, and we could scale them, and Moore's law took over, and we got more and more potential compute. I described to you 3 different kinds of quantum computer today. They were all radically different because there's not a good qubit yet. Everybody's trying to make the right qubit. They're exploring. Their quantum computers are very much like these bespoke general computers from the 40s and 50s. And maybe that's what it's going to take. My favorite story of this whole thing is one of the guys who made this transistor, a guy named William Shockley, he was also the guy who then created a company called Fairchild Semiconductor, and he made the first integrated circuits. And when he was trying to figure out the chemistry was going to need to dope it properly and what the ratio should be and so forth, he used an old-style mechanical mainframe to do the computation. And that gave him the models to be able to build the first integrated circuit that made far more reliable general-purpose computers. I wonder if these flaky, goofy, unreliable quantum computers we're building today are the compute devices we'll need to find the reliable qubit. I don't know the answer to that, but I like how the history rhymes. I do know this. When we're trying to predict the future, the best way to do it is to make it, and that's us. We do this. We're going to go out and do some work. These next couple of days, we're going to do a bunch of learning, and we're going to create the future, and I can't wait to see what we make. Thank you for your time.